Okay, we'll get started. All right, so I have posted homework 2. Homework 2 is available under week 3, and there's 2 parts. Part 1 is kind of like you've got an RMD file, and you'll work through that. You'll answer some textbook problems there. You should all have access to the textbook. You just need to be on the UCLA network. So you can either download the textbook while you're here on campus, or when you go home. If you're not living in the campus dorms, then you need to connect via the VPN. Okay, but as long as you're connected to the network, you should have access to these textbooks. And then you'll answer the textbook problems. That's 50 points, and then the other 50 points comes from the tic-tac-toe assignment. All right, and the specifications for how to write the tic-tac-toe are given in the RMD file. I also make some recommendations as to, because I wrote the assignment, I wrote a program myself, and so I was just trying to think, how would I break this problem apart into smaller chunks? And so I just have my recommendations, or at least just documenting what I did. Now, you don't have to do what I did, okay? You're allowed to do however you want to do it, but that's there, okay? And then I also posted a video of me kind of playing the game, and you can see how it works there, okay? I've decided to make it due a week from Monday, okay? So that gives you 2 full weekends to work on the assignment. That said, please start on it like today or tomorrow, okay? Don't wait till next Friday and then freak out about, how much work the assignment is, okay? It is a lot of work, all right? I mean, well, some of you have been coding for many years, and this is like a piece of cake, okay? But for many others of you, like your only other experience coding was Stats 20, all right? And so this assignment might be your first kind of programming challenge where you have to write over 100 lines of code, and so if that's the case, you want to start early. All right, if you wait till the last minute, it's going to feel like way too much work. Okay, but if you break it down into a few things, you just say, today my goal is to get my display function working, then you can do that. Okay, so I know the hardest thing in college is time management, right? So, or one of the hardest things, other than life in general. But anyway, we have that. Are there any questions about this? All right. Okay, then we'll get started on today's content. We're talking flow control, and we'll get into functions and scoping, and we'll see how far along we get. I think we started talking about the for loop already, and I said, probably your most common case is doing, for x or I and 1 through, some integer thing, but it doesn't have to be that way. And a for loop can iterate over any kind of vector, okay? If you use the kind of the integer for loop, okay? Integer vector for loop, you can use those integers as a way to subset and do assignment to store your results. And I think you guys are already familiar with this, right? Okay. And then we talked about while loops. And as far as while loops, you will need some kind of ending condition. So the loop will continue on until this ending condition is met. Okay? And so while loops are extremely useful and powerful. And in the case of the tic-tac-toe game, you will use a while loop. Okay? Most likely. All right? Because it's going to be while the game has no winner, or the game is unfinished, keep asking for turns, right? And then only when the game detects that there's a winner, or the game detects that, you know, the game has ended in a draw or something, then will it stop. So you'll have something while, and then you'll need something here, something like the game is not finished, and then keep playing, right? So that's how it goes. Because it's not, games could end in as little as 5 turns, but they might take all 9 turns to finish as well. So, so you don't want to use a for loop there. You want to use a while loop. Okay. The key with while loops is knowing how to properly set your ending condition and how to make sure your ending condition will eventually become false. Okay. Because as long as this thing is true, it's going to run forever, right? And so if you want a loop to run forever, then you'll just say while true, and it will run forever. Okay. So repeat is basically while true. Okay. Repeat is just is basically equivalent to having a while true loop. Okay, because then it will just keep running forever. And so both a repeat or a while true will run forever until it meets this statement that says break. And break just says stop the loop, okay? And so if you're gonna have a repeat loop, or if you have while, and instead of a condition, you just have all caps true, while true, which means run forever, you need to throw in some kind of statement that says break so that the loop eventually stops. And so here, basically the difference is I have moved this, this condition, that I is less than or equal to 10, into the body of the loop. So this part, you know, we're going to store I squared into the results and increment I by 1, okay? And that part remains the same, except the condition that says when this is no longer true, when I is less than or equal to 10, when I suddenly becomes greater than 10, that's when it's going to quit. We move that here. If I is greater than 10, then execute this line of code, break. And the break will quit the loop. Okay? And so we get the same results here. This and this will produce the same results. Is that okay? The while and the repeat, that's what we have, okay? So when you're dealing with...
Quick question.
Yes.
About the repeat, if you have 2 repeats, one nested in the other, and the break is within the inner repeat,
yeah,
will it break everything or just the inner repeat?
Just the inner loop. It just breaks the inner loop. I'm like 99.999% sure about that. Yeah, breaks the innermost loop. I guess I could write like a little thing, but yeah, break will... so if you have an outer loop and an inner loop, it'll break just the loop that it's in right at that moment, where the break is located. Okay. So in this case, we have 2 special keywords. One is break, which is just quit the loop, right? So if you're running a loop, break will just stop the loop. You might have 1,000 iterations left to do, but as soon as it hits break, it's going to say, I'm stopping this looping nonsense stuff, okay? And so here, I've got for I in 1 through 10, and then we say if I is divisible by 2, right? If I mod 2 is equal to 0, then break, okay? Otherwise, or not otherwise, if this thing is not triggered, then it will execute the next line of code, which will be just cat I to the screen, okay? And so here it runs, I takes on the value 1. It looks at this condition. The condition is false, so it does not execute the break, and it cats 1 to the screen. Then it reaches the end of the thing and says, okay, well, let's start the loop again. I now has the value of 2. It says if mod 2 is equal to 0, this statement is true, so it reaches break, and it quits the loop, and it's done. Okay, so it reaches break, it quits the loop, it does not execute cat 2 to the screen. So This is the result. It just prints out the 1. Okay. On the other hand, maybe you don't want to quit the loop, but you just want to skip to the next iteration. Okay. So in this case, if I have the exact same code, the only thing is I've changed the word break to next. Okay. So it's everything else is exactly the same. I've changed break to next. And so here, it starts off with 1. This is false, so it does not execute next, and it cats 1 to the screen. When it gets to 2, it checks this condition. This thing is true, and so it goes to the next loop. So it skips the rest of the code, and it goes to the next loop. And so it does not cat 2 to the screen. Then it gets to 3. 3 is false, so next is not executed, and it cats 3, and so on and so forth. And so by having this, it just prints out the odd integers where the next is not executed. Okay, is that good? Okay. There's other things we can do. So we said you can have the for loop run along any kind of vector. Okay, and so here we had this list which counts as a vector, and it would go through each element in that list. Okay. Now sometimes you want the index. Okay, and so in that case, it is useful to basically say, well, L has a length of 3, so basically I want for x in 1:3. Okay, and it will work through the the vector 1, 2, 3, and then rather than rather than saying the element, you can then subset the list using the double square bracket notation. Okay, so this thing is let me go all the way back to this slide. Okay, so here we just said for element y in list L, okay, and for the first time y is going to be the elements 1 through 3, and it's going to print or cat length of y. Okay, over here it's a little extra overhead, but we are going to iterate. X is not going to be the element y, but it's going to be the number 1, 2, or 3, and then we subset L using a double square bracket. We get the length, and then we're going to store it using the index into our results vector. Okay, and so the difference here is that we're not catting the results, but we are storing them into results, and then finally we printed the result. Okay, so it's a little bit different, and here we're just making use of the index. So sequence along is basically the equivalent of 1:length of L. Okay, so sequence along is just a shorthand, or I don't know if it's any shorter, it's the same number of characters, of 1:length through L. So both of these things do the same thing. I think when I was learning, this is kind of the mechanic I got accustomed to, is writing 1: the length of L. Okay, and it's always preferable to have this being dynamic. So if L suddenly became a list of 10 elements long, length L will adjust to that, rather than having it hard coded 1 through 3 and not being able to accommodate when the length of L changes. So 1:length of L or sequence along L, these are exactly equivalent. Okay, I'm actually curious. Maybe there is a slight difference. Okay, let's just see. You can always look at the code. When you type in the name of a function, you just delete the parentheses and it won't execute the code, but it'll actually tell you what the code is. Okay, but here it just says primitive, so that doesn't actually help us. And I think length is also a primitive, yeah. Okay, but some of the other things, like when you ask for So dimensions will pull up a primitive, but when you ask something like number of rows, the code is pull up dimensions of x and just give back the first element there. Okay, so you can actually see the code that runs when you do these things. Sometimes you get these dot primitives. Dot primitives means the code was written in a language that's not R, something like C or Fortran. That's actually the code that is running underneath R, and that's how certain computations are done quickly. So, okay, but anyway, 1 colon length L, sequence along L, or sequence length of length L these are all equivalent there. Okay. I don't know if you've heard this, but R is not the most efficient language out there, okay? But we love it as statisticians for a few reasons. One is it's pretty, like compared to other languages, it's pretty easy to write code in R, okay? It's dynamically typed, it's very forgiving, you can just coerce things very easily, whereas, other languages are a lot more strict and you have to do explicit type conversions. You can't just say like, what's the mean of this logical vector, things like that. So we love it for that. Another reason why we love R is because of the existence of NAs, okay? Being able to record something as a missing value explicitly, saying this value does exist, we just don't know what it is extremely necessary and useful for statisticians, because a lot of times our data has this. Other languages, like notably Python, which statisticians also love, Python does not have missing value. It has not a number, and that's what we often use as kind of a stand-in for a missing value, but then that requires everything to be of type double. So, or I guess in Python it's called float, but that's what we have. But anyway, one of the drawbacks of R is that it's not the most efficient, especially when you're doing things with loops, okay? So loops is like R's weakness here, and it's slow when it does loops. But a lot of times it's easy for us to think in loops, and so when you're writing code, go ahead and write the loops, okay? Later on, if you can make it efficient by writing vectorized code, then do that, right? So all of these things, like we were writing like for I and 1 through 10, and we were basically saying, I don't know what we said, print I squared or something like that. Or here, actually, let's say x is 0, and then we're going to say for I in 1 through 10, what we want to do is x sub I is, I squared. Okay, and then x becomes this, right? It's much easier, all right? It's much more quick if you just did 1 colon 10 squared, okay? And then so this is the vectorized operation, okay? And then this is a loop. The loop iterates, it has to run. Each cycle has to go, I is 1, we square it. I is 2, and we square it. I is 3, and we square it. And computationally, this method takes a lot longer than this. Okay, this is much faster. I mean, I don't know if we can. We'll just see how long this takes. So if I'd say I through 10 is 1 through 10 million, you can see my computer's tied up for a few seconds. Okay, so it finished now. Whereas if I just change this, y is the vector 1 through 10 million squared. It's done now. And I don't know if you noticed the difference in the computation time, but the loop took longer than the vectorized operation. Okay. I mean, it's hard to calculate what is the last element in okay, a big number. All right. I don't know what I was expecting, but yeah, okay. So anyway, it computes all of these things. All right. So anyway, but the one you can get working, that's the best, And then once you get it working, then you can worry about making it efficient, okay? If you try to make it efficient a little bit too early, you might make headaches for yourself. All right, now we got to talk functions, because this is very, very important. You should get in the habit of writing functions, okay? And what I mean is this, and maybe I'll add a line of code here, or a slide here, is that if you find yourself doing a task, like you wrote like a short script, you know, like maybe 3 or 4 lines of code, and then you say, okay, and I need to redo this, but now for a different variable or something else, and you find yourself copying and pasting that line of code, that chunk of code, to do the exact same thing, okay? The rule of thumb is if you copy and paste it once to do the same thing for another variable, if you copy and paste it once, that's fine. If you copy and paste it twice, you should start thinking about a function. And if you're going to copy and paste it a third time, you definitely need to write a function, okay? So so that's kind of your rule of thumb, all right? And that's where functions come in. Instead of having to just say, I don't know, let's say you're dealing with some kind of, you're downloading data from a website, right? Except the stupid website says like, okay, here's the data for January 2018, and here's the data file for February 2018, and here's the file for March 2018, right? And so you might say like, okay, how do I get this in? I've got to process this. First I'm going to do read underscore CSV, and then once I do that, I'm going to change the names of the things to say, you know, we're going to add a column so it says January 2018, and I'm going to do this and I'm going to do that, okay? And you say, and then you have like 6 lines of code, and you're like, okay, this worked great. Now I got to do this for February, and then so you just say, okay, well, what did I do? I'm going to just copy and paste it, and then I'm going to change all the Januaries to Februarys, and then you say, okay, and I got to do it for March, and you copy and paste it. You don't want to have this thing where you got 12 chunks of code going through every single month, okay? By the time you're copying and pasting it the second time, you should say, maybe I should turn this into a function, okay? And if you're going to do it a third time, it definitely needs to be a function. You've got to just write a function that says, okay, we're going to do this, and you're going to take in a variable like January, like an argument, it will be month name, and then you do it for January or something. And that way, later on, you find out, oh, you know what? I need to also add this one other column or something. You don't have to modify that line of code in all 12 locations, okay? Because that's going to be error prone. Instead, you just say, well, I wrote a function. I just need to modify my function a tiny bit, and then you just run it for all the different months there, okay? So I'll throw a slide in here, okay? But basically, functions are useful for this reason, and we create a function like this, okay? All you do is you say, I'm making a function, and it's going to have arguments. It's going to have some kind of expressions, commands to execute, and the function ends with a return statement, okay? Or it might not have an explicit return at the end, but functions generally return something, okay? And then this will create the name of the function. So functions themselves are objects, and you can store them inside lists and things like that. And if you ask for the type of, it's known as a closure, okay? Don't worry about this, but because functions themselves are objects, you can have a function return another function, okay? I debate whether I want to, every time I present this, I'm like, maybe I shouldn't present this, but it's just kind of a neat thing. But okay, the important thing of a function is that it takes in inputs and it returns something, okay? Generally, you identify a function using curly brace, okay? To say, you know, this is the start of the function and this is the end of the function. But just like if statements, if there's only one line in the function, then you don't need to put in the curly brace, okay? But I guess this is, I should probably get in the habit. All right, maybe I'll go in and I'll modify these things. But here, I'm going to create a function called f. F receives one argument, x, and the value it returns is x times x, okay? So this is basically, multiply x by itself or square it, okay? Here I've explicitly used the statement return, and when it does this is, you put x into the function f, and f will say, okay, I've done what you asked me to do. Here is the value back. That's the value that it returns. Okay? If you don't use the expression return, then the very last statement that appears in f is going to be the value that it returns. Okay? So these two functions are equivalent in that they are both going to return x times x. Okay? The key thing to remember is that a function is only able to return one object. Okay, this is a key thing to learn in R. It's not like this in other languages, but in R, when you can give it multiple input values, but it will always return only one value. Okay, it will return only one object. So if you want multiple values returned, you need to group them together into a single object. So for example, let's say we want to get back the value x, x squared, and x cubed. I cannot return all three objects separately. I have to group them together into a single object by just using the combined function c, okay? And so this is an implicit return, right? The function x will return this object, this vector, which has grouped x, x squared, and x cubed. And so when I say, what's the function applied to 2? It gives me 2, 4, and 8. Yes, question?
Is that different than cat?
So cat, what does cat do? Cat just outputs to the screen. Cat does not return an object, okay? Like, I think in your homework, when you asked, what's the result? Like, let me store the result of cat. It stored null, right? And that's the thing about cat. Cat does not return an object. Okay, it outputs to the screen, but it doesn't return an object here. Okay, so here, let me just kind of demonstrate. So we're going to define this function f. Okay, and so maybe just to be better about the code here, okay? So all f is this function right here. And if I say f of 9, it gives me back 9, 81, 729, right? And so here I can say, let's store f applied to 9 into the vector y. And I ask, what is y? And it gives me 9, 81, 721. Okay. On the other hand, if I just say, let's cat 9 squared, and 9 cubed, okay, the output looks similar, but if I stored this into z, z does not have a result. Okay? So you can't store the output of a cat. Okay? Whereas when I store the result of f applied to like 10 or something like that, I can store this into z, and now z has these values. Okay, so a function takes in an input and it returns some kind of output value. All right, and if you want multiple values returned, you need to group them together. All right, and so in this case, because all the values being returned are numeric values, I can just combine them together easily. On the other hand, if you have different kinds of things, you can also return a list. Okay, so here is a function, and what it's going to return is a list of x, x squared, and x cubed with the names x, square, and cube. Okay, and we can then store this result, this list. Okay, which is what the LM function does. So when you create a linear model, you can read all the code that it's doing, but basically it's producing a list called z. Okay, it produces a list called z, and this very last line of code says we want to return this object z. Okay, and you can see the things that it does, right? Z $contrast, Z $call, and z is going to be a list. When it first creates it, it's going to say z is going to be a list where the coefficients is this, and store these things into the residuals and these things into the weights and stuff like that. Okay, so not to worry, but this is how functions work. Okay, they take in an input, they return a single object. And so in this case, I can apply the function f to the vector 2 through 4, and it will return all of those things, right? X is 2 through 4, square is 2 through 4, quantity squared, 2 through 4, quantity cubed, things like that. When you specify a function, you are defining the names of the variables. Okay, so here's function x, y, and z. And what f is going to do, this function is going to paste x equal to the value x, y equal to the value y, and z equal to the value z. And so when I run the function 1, 2, 3, it's going to take 1 is x, 2 is y, and z is 3, and it's going to plug in that value 1 right here, and it's going to print out x equals to 1, y equals to the second value 2, and z is equal to the third value 3, and so it prints that out here. You can, when you call the function, you don't have to use the same order here, so you can say z equals 1, x equals 2, and y equals 3, and when the function runs, it's going to say, all right, first I'm going to print out x equal, and it's going to look for the x value, and in the kind of the list of arguments that you provide, you've told it x is 2. So it prints out x is 2, y is 3, and z is 1. Okay? So you can kind of mix up these things. If you specify one of these things, y is equal to 2, then it will figure out the assignments later. It'll say, okay, well, x has to be 1, and z has to be 3 in that case. And you can kind of mix up these things this way, right? And so this works, and if you give it an argument that it doesn't know, it's going to say m is 1, and there's an unused argument here. You can also give it some default values. You can say x is 1, y is 1, and z is 1 as default values. So here, we just define the function x, y, z, and over here, we're given it default values. So that this way, you can run the function without providing it any arguments, and it's going to say, well, I'm going to just assume x, y, and z are all the value 1, okay? Because that's what we said in the default arguments. And now if I say f of 2, it's going to take 2 and assign that to the first argument x, and it's going to return x is 2, and it will take on the default values for y is 1 and z is 1. And likewise, you can just specify one of them, and it'll take default arguments for the things that haven't been specified. Okay. I guess this kind of just reiterates what I said about when to use functions, and it's used to kind of redo some kind of task, a piece of code that you might have to apply more than once. Okay. Here's the important thing about functions and scope and environments is that when you execute a function, the only way the function interacts with stuff in the environment is through the return value. Stuff comes in the argument names, and then something goes out through the return value. If you modify things inside the function, those things exist only inside the function. So when you execute a function, it's like it creates its own little sandbox, its own little secret closed environment. It runs all the stuff, and then it says, this is the value I'm returning. It sticks that out, okay? And then everything that was in this sandbox, this environment, disappears, okay? So if you didn't return that value is gone. And the thing about these environments, though, is that you can reference names that don't exist inside the environment. And R will employ its scoping rules to kind of search for these things, all right? So this is generally not a good idea, but the function will execute. So here, I've defined a function of x, okay? And the function is going to return the value x plus y. So this function references some object y that has not been defined as one of the arguments coming in, okay? And so when R encounters this, it will search for the value x, okay? And then it will search for the value y, okay? It will have the value x because it's one of the arguments coming in. When it searches for y, it's going to say, this does not exist inside my sandbox. I'm going to search in a higher scope or in a higher environment, okay? And so in this case, when I call f of 3, x takes on the value 3, and it says, I need to return the value 3 plus y. And it says, I don't know what y is. Oh, I found it. Y is the value 1. And so I'm going to return the value 3 plus 1, and it returns the value 4. Okay? Here, I still have y is equal to 1 outside in the global environment. And inside, I'm creating a function. It's a function of x. Okay? And inside this function, I create something where y, and I write this command, and I say, assign the value 2 to y. Okay? The last line of the function is x plus y. So it's going to return the value x plus y. So I call g of 3, g executes, and x takes on the value 3, because that's what we've provided as the argument value. And then it says, return the value 3 plus y. And so it looks inside its own current environment, and it says, oh, y is the value 2, and it's going to return the value 5. Okay? So here's a question. In the global environment, if I ask what is the value of y, is the value of y 1 or is the value of y 2? Okay, the value of y in the global environment will remain 1, okay? Because I'm going to delete everything in my environment, and here is the code we're going to run, okay? So y in the global environment is 1, but g of 3 will return the value 5, okay? And it does not interfere, it does not interact with the y that is defined inside g, has nothing to do with the y in the global environment. Okay, so I think this is what I said. Variables defined within a scope only exist in that scope for the duration of the scope. Okay, so you can think of these things. So if, like for example, within the function, you execute the command rm list equals ls, which is what we use to delete everything in the environment. This will just only delete the objects that have been defined inside the function, and it will have no effect on the values in the global environment. Okay. You encountered the superassignment operator inside in your first homework assignment, and that is an exception, and this will assign values to the higher environment. Okay. So here's some examples of how these scoping rules work. Okay. So here I've got x, y, and z take on the value 1 in the global environment. Okay, I'm creating a function f, and within the function f, I'm creating the function g. Okay, inside the function f, y takes on the value 2, and inside the function g, which is defined within f, z takes on the value 3. Okay, and here, g is going to return the value x plus y plus z, and and we want to know return the value of g, okay, when we execute f. So I say execute f, f returns 6, okay? And if I ask what is the value of x, y, and z in the global environment, they are still the value 1, okay? Because when I execute f, f is going to say, this is the order that the code operates, okay? F is going to say y is the value 2, and then it says, all right, we created a function g, but I don't actually care about it, okay? But then when it gets to return, what does return g, then it goes, oh, well, I defined g, let's run that code g. So now it says z is 3, and we're going to return x, which we don't see here, so it searches the higher scope, it doesn't see it here, so it searches the global environment, and it takes on the value 1. Then it says, I need the value y, and it searches here, and it doesn't see it, it searches here, and it takes the value 2, and it adds that. And it says I need the value 3, and it searches here and it finds it, and it does 1 plus 2 plus 3, and it gives back the value 6. Question?
Are these swapping properties like controversial at all? I would like those into the previous.
Is it controversial?
Like, is this normal?
This is how R decided to handle scope. Okay, the people who write a language will have these philosophical arguments of what it should do, right? So in other languages, if you say, all right, let me have your attention, please. If you say return the value x and y and z, and they are not defined inside the function, it's going to say, I can't do this. Okay, you're asking me for values that don't exist in the function. R decided, you know what, we're going to be a little bit more generous, okay? If you call for the value y and it's not defined inside the function, we'll say, you know what? He probably meant to put it in there. He's probably referring to something in the global environment, and so we're going to have these, okay? But this just means now you need a system of rules to follow so that the behavior is predictable, okay? And if you understand the rules, everything is predictable, okay? It's just because the language of R is generous in this way, there is a certain set of rules that we have to follow, okay? And that's what these slides are trying to teach, okay? So yeah, depending on the language, this might not be allowed. It'll say y, I don't know what y is, okay? And you might be like, no, I have it defined over here. Can't you just use the one I've defined over here, okay? And the other language, no. In R, yes, okay? So, but x, y, and z remain unaffected. So even though we've assigned 2 and 3 inside these functions, they remain unaffected and stuff like that, okay? Okay, so again, in the global environment, x, y, and z are 1. And notice here, okay, y has, we do 2 superassigned to y. And inside a function, f, I create the function g, and I say 3 is superassigned to z, okay? And so what this does is that this runs, and it's going to take the value 2, and it's going to say, don't assign it into this local environment, but go into the global environment and change the value of y in the global environment to 2. Same thing here. It's going to first search the higher environment, and it's going to say, well, I don't see a z inside the scope of f, right? So you've got the global environment. Inside the global environment, you've got a sandbox called f, and inside f, you've got another mini sandbox called g. So when you say z superassigned 3 to z, it's going to search the sandbox for f, and it's going to say, z, is there a z in here? It's going to say, I don't see z here. Let's keep searching higher. And it gets to the global environment. It goes, oh, I found z. Z has the value 1, but we're going to replace that with the value 3. Okay? So when it runs this, then it returns x, y, and z. It's going to say, let's search for x. X doesn't exist here. X doesn't exist here. X only exists in the global environment, and it has the value 1. It's going to ask for y. Y doesn't exist here. It does not exist here either, because this directly assigns to the global environment. And so it takes the global environment value, which is 2. And same thing with z. It searches for z. Z does not exist here, because these directly assign to higher scopes. And it only finds the z in the global environment 3, and it returns the value 6. And when we ask for what is x, y, z, it says 1, 2, 3. Yes, question?
So it's defined to the global environment, and if you don't have x, y, and z be 1, then it will use 2 and 3? Like it'll search this one, won't find it because it's defined.
So what happens when, okay, so let's say I never defined, let's say I only defined X, okay? Because if I don't define X in the global environment, it's gonna crash, okay? What this super assignment will do is it keeps searching higher things, and then if it reaches the global environment and still hasn't found it there, then it will create it.
But it is there.
It is there and it overwrites it, okay? So it keeps going higher until it finds it, and then it will change that value. So I think, okay, so here is, I think this is the example that maybe will help, okay? I've got, all right, this is the last one. Let me just have your attention here, okay? X, Y, and Z are defined as 1 in the global environment. Within F, I create a local value of Y called 2, and I use the super assignment of 4 to Y. This super assignment of 4 changes this Y in the global environment to 4, okay? Here I have superassign 3 to Z inside G. So it's going to, when it runs, it's going to search for Z in F. It does not find it, and it changes the value of Z in the global environment to 3. It asks, I want the value of X, Y, and Z, okay? It's gonna search for X. It doesn't find it here. It doesn't find it in G. It doesn't find it in F. It goes to the global and it takes 1. I ask, search for the value Y. It doesn't find it in G. However, it comes to F and it finds the value 2. So it does not bother searching the global environment. In the global environment, Y is now 4, but it has found this value of Y, which is 2, inside of F. So it's going to use 2. Then we ask for Z. It's not found here. It's not found here. It's found up here, and it has the value 3. So it's going to return 1 plus 2 plus 3 and give back 6. However, when we ask what is the value of X, Y, and Z in the global environment, it's 1, 4, and 3, okay? The first time you're encountering this, which I imagine is today, this will feel really, really, really weird, okay? The rules are there, they all make sense, and it always follows the rules. If we understand the rules, this stuff makes sense, but in the beginning, it's strange. Okay, we'll end here. We'll see you guys on Monday.